Welcome to our class. We did last week language of the universe is definitely mathematics, is mentioned by Leonardo da Vinci and Galileo Galileo. And as first definition is variables. Then while we are using the variables, we can introduce some statements, but these statements could be definitions, causal statements, decisional ones, or logical statements, depending on the structure of the statement. Okay, and to learn the mathematical terms and terminology, we have to be able to read the properly mathematical expression. For example, a square plus b square is equal to a plus b in parentheses and squared up. And or are the numbers a and b such that a square plus b square is equal to a plus b in parentheses and squared up. Do there exist numbers a b such that satisfying this equality sometimes is used satisfying this equality, or for any real number r square is positive or non-negative, or square of any real number, you will get positive number, positive integer or positive real number. For all real numbers, r square is positive. There's different sentences using the mathematical terminology. When we're talking about the statements, we can differentiate three subclasses. As one is universal one, the other one conditional, the third one is existential statement. A universal statement, we need a quantifier like descriptive one is all. Here, all positive numbers are greater than 0. Conditional statements, certainly you should be looking for if and then, whatever the this is the hypothesis, this is the could be consequences or result or argument to be judged or to be decided later. And the existential one is required at this one thing there is a prime number that is even, there exists even prime number. In that case, one example is one satisfying prime number is enough. Now, repetition of the last week. And language of sets is built by Cantor. We talked about in the class. Roster notation is this one. And we talked about axiom, theorem, and lemma last Tuesday, first week of this semester. And we talked about Norbert Wiener and Krotowski about the Cartesian product. And how can we construct ordered pairs or numbers? We will see a few weeks later. Talk about this one, Cartesian product. I gave the examples. Maybe you should remember. You should remember this graph as well, graphics. So last week, where we stay with the question of as an working question. We have the data and information is vastly and provided in the internet. We can reach anytime. But knowledge mainly is the experience. This cannot be transferable. And that's why, what was my question last week? Is cannot be transferable. Then how can we get knowledge or experience? That was the question for next Tuesday. And then we will start next Tuesday to the logic of compound statements, and basically first philosopher could be Aristoteles, is deductive reasoning introduced, and later on in 17th century Leibniz used some symbols and mechanized the process of deductive reasoning, part of the logic, symbolic logic language. But most importantly, George Boole and De Morgan, Augustus De Morgan is most very important scientist, established the computer logic as well. Boolean algebra or Boolean logic is very famous for the computer scientists and computer students, and discrete mathematics as well. In the 18th century, or very important establishment for the automatic machines and computer by George Boole. And we have to talk about the logical equivalence and logic forms. One of the famous example, if x out of is less than minus 2 or greater than 2, then x squared is greater than 4. When you negate that, negation, take the negative of this logic is x squared not greater than 4, then both of the assumptions are not valid. Be careful here, or, and it's translated into the and, right? It's very important. Or compound statement, P or Q, then R. Therefore, if not R, if not, then not P and not Q. It's very important. And this is or and this is and. This is the way De Morgan rules working. And you can work on it. What does misstatement or proposition, as in a philosophical way, is a sentence that is true or false, but not both, okay? It should be either one of this, true or false. Compound statement is conjunction with and, P and Q, or disjunction as P or Q. And this is the symbols, this is and, this is or symbols, okay? This is the complement or negation, not order of operations. First, we have to apply the negation and then and or, okay? And that's it. Yeah, what does mean P but Q is P and Q. Neither P nor Q means this one. And just negation we have, negate the or, and we will get and here. Here we go. It's not but it's sunny. It's neither hot nor sunny. This is the way you can write it down. This is the logical expression. The important part is inequalities. We will be using in mathematics a lot. X less than or equal to A means either less than A or X is equal to A, or for interval estimation, for interval, this is mathematical number interval, it means X greater than or equal to A and X less than or equal to B at the end, okay? This is the important logical expressions. Oh yeah, this is Q or R, this is and, and or. Of course, this is or. This itself is less than or equal to 3, this one, right? This is less than 3, this is equal to 3, and this is greater than 0. This is less than 3, this is greater than 0. This is again greater than, less than 0, less than 3. This is the truth table. What does mean truth table? You are putting the every possible truth inputs for P and we have only one logical input, then we have only two cases here, true or false. There is nothing else more. And it's the negation, and negation is complement or sometimes is opposite, reversing the process. So T as F, true goes to false, false goes to true. Very simple. Conjunction is AND, you know that. And only case is true in conjunction or AND. Both of them are true, then we can talk about it is true. All other cases false. We need true, true, and true. Inclusive OR, we will see the exclusive OR called disjunction at the same time. This is the OR. We have triple true and only false. We have both of them false, then we get the false sign here. XOR is used in the digital logic and computer logic very well. And if and only if conjecture. And this is the way we can obtain this from the known OR and structure. When you do this, you will get true whenever there are inputs if two different cases, true, false, or false, true. False, if both of them are equal, true, true, or false. Be careful. This is XOR, used a lot in the digital logic implementations. Truth table is like that, you know. We have OR, only one false. We have AND, only one true. A negation of AND, of course, this goes false, the other ones are inversed. And when you do everything here, with this one and with this one, true, false, true, 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 it's double true here, and the other ones false. Yeah, you can extend these truth tables by triple. If we have one logic input, 2 to the 1 is 2 option. If you have 2, 2 to 2 is 4 option. Second power of 2 is 4. If you have 3 input, this is the case here. Third power of 2 is 8, right? 1, 2, 3, 4, 5, 6, 7, 8. First variable is 4 true, 4 false. Double 2, double false, and true, false, true, false. This is the way you can obtain the truth tables, structured truth tables, of course. So whatever you asked or requested, you can obtain easily by following the AND or negation signs. Okay. First, order of processing, order of operation. You have to first apply the negation, then AND or. So, logical equivalence means the truth table giving the same value, like this one. This is the same. These two operations are called logical equivalent. Double negative property, it's the same. Negation cancels themselves, and this is the way. Double negation is nothing. Showing non-equivalence. This is not equal, it's not non-equivalent. De Morgan laws is very simple given. And negation of and or negation of or and. The other inputs should be negated as well. Very, very simple one. High school level. This is De Morgan law. Yeah? We have plenty of examples here. This is the important one. X greater than minus 1 is less than or equal to 4. When you negate that, what is the negation of less than sign? Greater than equal to. What is the negation of this one? Of course, greater than. Then you obtain this one. Okay? Be careful about that. This is the interval, or a couple of intervals. Then you will get complement or negation of that. As you can see on the number line. Tautology is very well known in logic. It means the truth table, every entry in the output is true. Vice versa, contradiction is every value in the output column should be false. This is contradiction and tautology. For example, tautology, this one and this one is contradiction. It's very simple. Take P and negate P and then apply these rules. Very simple. When you obtain the last column, all false or all true, then you can talk about tautology for all true values, all false values for contradiction. And this is an important table. You should take care of it. Whenever you see T is means tautology, it's very simple. Everything P and T, wherever you put here P and T, whenever P is true, this is true, right? Whenever P is false, this is false. So it is P. Or whenever C all the line is a column is false. False, false is false. True, false is true. Yeah, this is the correct. Is satisfying the equation or equivalence relation here, right? And this is very well known tautology, and this is very well known contradiction. You can do it by showing these all equivalence by truth tables. T means every column, and its column as consisting of all true. Capital T here, capital F here. And this is the simplifying. It's very simple, and this is just negate, cancel each other. You obtain P, and this is the way you obtain this one. When you do this, this is a distribution property. What does mean distribution? Or distributed over N. When you do this, this obtain is contradiction here. It's written, right? This one, contradiction. When you put contradiction here, again, you will obtain and P. So it's equivalent to P. Check the table. We use first this one, and then this one to reduce the equations. What does mean conditional in English as well? If in the English language the same. If we have the if and then, if clauses or in English literature, we are talking about conditional statements. Could be any inference or deduction, hypothesis and conclusion. This is the hypothesis, this is the conclusion. It doesn't matter. If P, then Q. P called hypothesis, Q is called conclusion or consequences. And this is the way, this is if then. P then Q, right? This is what you call if then truth values, right? If you can read if P then Q. This is the way you can read this sign, all right? It's connective. And order of operation, first negation, second is and then or, third is if then, right? When you use the if then, the truth table looks like that. When then two inputs are different, the only false is first one is true, the second the hypothesis true, consequence or conclusion cannot be false. This is the way you obtain this false, okay? This is the only way you can obtain false. All other three is true. Conditional, hypothesis or antecedent or conclusion or consequent. We talked about that. This is the order of logical operations, okay? The last operation is this one. This is the equivalence relation and negation. You can work it out. And division into cases. This is the way you obtain this one, and this is the truth table. So these are two equivalent. This is the P or Q if then R. P if P then R, and if Q then R, and conjuncted by conjunction by and are the same. You see, these true, false, false are exactly the same column, and this is logically equivalent. In this reverse way, this could be a reduction or this is the way extension. This is the way a reduction is. Could be used both, right? Whatever is good for you, you can use it both. And this is the simplest case item. So the way you can obtain simple expression. And you can, anytime you can translate it into OR connection on this junction with this, not P or Q. This is the same, right? Of course, when you negate them, you will negate this one. What about negation of this? This is negation of negation P is P and Q, not Q, right? Not Q. P and not Q, right? This is the way you obtain De Morgan laws as negations, contrapositive. Contrapositive, we will talk about a little bit in the class. This you can work it out. It's very important topic in mathematical proof. Please work on it, okay? Very, very important one. And converse is just simply changing the hypothesis and conclusion. Inverse is negate both of them without changing the substitution of the places, okay? That just negate that. Inverse is negation. Converse is replace them, okay? Be conditional is if and only if, and we will see that. This is the truth table. Be conditional means when you, two different input, when the input are different is false, the same is true. This is if and only if. And it's used a lot in the all proof mechanisms. When you go this side, from P to Q is sufficiency, from Q to P is necessity. When you're doing bidirectional proof, and next week or following weeks, we will see that if and only if very important part of the proof. But at the same time, is the part of the logic. This is the way. And order of operations. Yeah, we talked about that. First this one, and then this one. The third one is the if and only if. We call if I and double F. Don't forget this notation. Right? We'll talk about this if and only if. Yeah, this is the sufficiency part. This is the necessity part. Very important for the proof for next week. Now, this is an optional part, but you have to think about the computers. Why? Because everybody using that, and this century is algorithms century, called last century called transistor century, and this century is algorithms because of the AI. But we have to know what is the rules behind the logic in the computer, and let's try to understand that. Digital logic circuits, this is very important. Scientist Claude Shannon established the information theory, MIT graduate student, and very important part of the not just information theory, but internet theory. And currently we are using internet. Theory behind internet started with Claude Shannon. And this is the practically John WTK is implemented this CPU Intel Durbin. It's very, very important. 4004, first available CPU for small applications, different than mainframes by that time. Very, very big computers. Only the very expert ones can use the computers. But after Intel 4004, it's changed a lot, and some small applications, all engineers try to begin to understand what's going on in the CPU and logic side, not just expert ones. But it's basically digital logic gates and truth table as we previously stated, and complex logic circuits. And then started with George Boole, and Boolean expression is the first course you have to take digital logic and electronic engineer, for example, or computer engineer. It's very important. Boolean algebra. And you have to know binary and hexadecimal system. Or NAND and NOR gates, very important for computer circuits and electronic circuits. It's developed later on with the development of MOSFET. A binary representation, obviously you have to take care of that one, because computers knows only binary and hexadecimal value for current computers, of course. I'm not talking about the quantum one. This is the way you can work on it. Adder, multiplier digitally is implemented in the chips or software commands, depending on the topology and the configuration. RISC architecture or KISC architecture for computer. RISC is implemented in hardware, every operation, logical and arithmetic. KISC is software implemented computer. Hexadecimal notation, you have to know it. ASCII codes is everything is in. You see this? This is the way you obtain the hexadecimal code and ASCII code. And you can translate anytime to binary. It's easily. Adder is not a problem, but multiplier circuit is much more complicated. It needs some electronic improvement. Thanks a lot for this second chapter, and next video we will be talking about logic, quantified statements, and chapter 4 is the type of proofs like direct and indirect or proof by contradiction. It's used a lot in the mathematics and all kind of engineering. Okay, thanks a lot.